All right, so we're going to give this first problem here a try. It looks very scary, but we're going to try and just kind of simplify it a little bit and just kind of see what we can do. All right, so it's asking to propose a mechanism for the following reaction, okay? And it's basically saying that this is our end product. How do we get to that point? It's kind of step by step, okay? And we're adding H2O and a hydrogen ion. I don't really know why. I think it's technically called hydride, I think is H minus. But anyway, this is really nothing other than hydronium. We're adding an acid to an alkene, which, from what I understand, makes an alcohol, which we can see because of this hydroxide group here, okay? All right, so let's look at this. The first thing that you always want to do with an alkene reaction is get rid of your double bond, because obviously the big differences between here, or this whole model and this whole model, is that the double bond is broken, okay? So remember that the double bond is nothing but a pair of electrons. So this pair of electrons is going to be like, all right, well, we're broken off this double bond, but what are they going to mix with? What breaks that double bond? What happens? Well, it's always going to interact with a hydrogen. And remember, since these are electrons over here, this is our nucleophile. I think of that because Nick Foles is a quarterback, and Nick, for nucleophile, he's sending his electrons. He has the football or a double bond or whatever, and he is sending his electrons. He's getting rid of the ball, okay? So he needs to find an electrophile. A lot of time electrophiles are positively charged. And, well, here's a positive charge right here. Let's take one of the hydrogens from this hydronium, and we'll bring it over. So let's do the first step here. I also think Zach Ertz is the receiver, and E for electrophile. So we know our double bond is broken. And we have two methyls. Okay, so, and I like to think, too, of the electrons kind of Spider-Manning and saying, hey, hydrogen, you're coming with me. I'm going to bring you back. So we need to figure out, where does the hydrogen go? And we have two options. Is it going to go here, or is it going to go here? And remember that it's not drawn here, but there's already a hydrogen sitting here, and there's already a hydrogen sitting here, right? 1, 2, 3. These are sp2 carbons. The other thing we want to keep in mind is that with an alkene reaction like this, sp2 carbons become sp3 carbons. And we can see that in the final product because the carbon that we started with, this one, is now attached to 4 things total. And this is attached to 4 things total because, again, you can't see them, but there's a hydrogen there and a hydrogen there, and there's going to be a hydrogen there. Okay, which means 4 electron domains, which means those are sp3. So that lines up with what we're looking for in this reaction. Okay. So back to what I was saying here is that we broke this double bond. Both these H's are still technically here. However, just looking at this now, 4, 3, 2, 1, this is not correct. I'm just going to draw this for a second. But these both would technically have a positive charge. But what we basically have is the hydrogen that we took from here, and the double bond. This is what we have to work with. This is what we're introducing. Where do we want to put that? And obviously, since this is a pair of electrons, it's going to reduce one of these positive charges. But where does the hydrogen go? Where do we want to put this? Well, it's not necessarily where does the hydrogen go, but we want the positive charge to be on the more stable carbon. And what stabilizes carbon is these overlapping orbitals of other alkyl groups. So look at these methyls here. This and this. These are going to stabilize positive charge. So we need to look at where is the closest place to all of those methyl groups. That's going to be the best place to put the positive charge. That is why we keep the positive charge there, and we introduce our new hydrogen here. Okay? And that gives us an sp2, which is already one of our final products here, okay? Okay, but now we look at this, and remember, what we've created now, this is called a carbocation. And you have to ask yourself, well, can this carbocation be in a more stable formation? And it can, because this was a better option to put a positive charge on than this. But an even better option for that positive charge would be up here. Because this is attached to 4 things. This is an sp3. This is only an sp2. So what's going to happen is what's called a methyl shift. And this positive charge is going to be like, I want to go somewhere else. And these methyls are like, okay, well, we can trade. And what happens is this methyl group is like, okay, let me come down here and let's bring the positive charge up here. And let's kind of see what we have. Let's kind of see what we're looking at. So the next step in this, 1, 2, 3, 4, 5. I'm just going to keep everything where we have it, because it's important to know where everything is. Well, let's not look at that for a second, but what's going to happen is one of our methyls is going to shift down. The hydrogen that I was just about to write, this hydrogen, let's use a different color. This hydrogen, we're not getting rid of. I'm just going to put it here. So this is now a methyl group. This, I'm now moving here. That's a methyl group, okay? And if we look at our carbon that's here now, it's now sp3. It's attached to 1, 2, 3, 4 different things. Perfect. That's exactly what we want. And it doesn't have a positive charge because the carbon is attached to 4 substituents, okay? But what we do have now is an sp2, and the positive charge is now going to sit here. This is just a more stable way to write this. And you're probably asking, well, the positive charge was already attached to 3 substituents. Now it's attached to 3 substituents here. So why is this more stable than this? I'm really not sure, to be honest, but I think it just makes more sense to have the positive charge now be close. It has this carbon stabilizing it. It has this carbon stabilizing it. It has this carbon stabilizing it. It's just a better location for it to be. I'm pretty sure. Okay? All right. So now what happens is we can't forget about we got rid of one of our hydrogens, but we still have an H2O remaining. And remember, an H2O has 6, 5, 4, 3, 2, and then 1, 0, has some lone pairs to give, all right? And this is a clear sign that this is a nucleophile. What does a nucleophile want to do? Well, it wants to send its electrons to a positive receiver. And what do we have here? Well, we have a nice positive receiver here. So what's going to happen is that we're going to just send a lone pair here, but rather than, we're not going to a hydrogen, we're not pulling a hydrogen, we're going to attach this whole water molecule to this section here, okay? And this is going to be kind of a little messy, but what it's going to look like, we already know we're getting rid of this positive charge. So let's just get rid of that. But what are we getting rid of it with? We're getting rid of it with a pair of electrons. We're going to put this here, okay? So that is a pair of electrons. So what do we have left? We have an oxygen and we have two hydrogens. Okay. Now, is there a charge here? Because we also brought over a lone pair. 6, 5, 4, 3, 2, 1. So I hope I'm doing this right. 6, 5, 4, 3, 2, 1. I do see a +1 charge here. God, I hope so. Yeah, that makes sense because we got rid of one lone pair. That makes the bond. And we brought over the OH. But I do 6, 5, 4, 3, 2, 1. I am still seeing a positive charge here after we're done. This is where I think I get a little stuck. Let's see, because we have this. We need to get to the OH. So we're literally just one step away. We need to get to this. Everything else is in place except we need to lose a hydrogen. I think what happens is because this is like excess water or something, another pair of electrons from water is going to neutralize this positive charge again. It's going to neutralize the positive charge. We get rid of the charge. Yes, so here's what's going to happen. Running out of colors. A lone pair, it doesn't go to the positive charge, but it's gonna Spider-Man a hydrogen, and it's gonna pull a hydrogen away. And it's going to form, if we're adding a hydrogen, H2O, well, it's gonna form H3O plus again. It's gonna form hydronium again. But the result come on. Let's just draw this. The result, that O will still be there. And 1H, which, hey, look, that's our result. There was a lone pair that was already sitting there. But when we pull this hydrogen back, this pair of electrons is going to collapse into oxygen, which gives us this. 6, 5, 4, 3, 2, 1, 0, which gives us a neutral charge. So our final result is going to be hydronium plus this. Let's see if we got that right. Okay. So this was the methyl shift we were talking about. This is the first step. Yep, we had the positive charge on the more stable one. So H2O was still in there. I didn't write that part. We did the methyl shift. The positive charge, was that at the top? Is that where we put it? Yep, that was our methyl shift. Then we reintroduced our water, and we said, okay, let's nucleophile, Nick Foles to Ertz, neutralize this positive charge. And just like we expected, we had an O and two H's. and we just counted our charge. We followed our electrons. We knew we had a positive charge. We introduced our water, which I'm a little confused on, but I think it has something to do with like this is excess water, so you can use it a couple of times. Don't quote me on that. But we're using this water here. We're using this water again. Slingshotting a hydrogen, bringing a hydrogen back. That's why we get H3O plus. Electrons collapse into the oxygen, and that's why we get this product. So this is number one. Jesus.